have much in the way of major announcements other than you all just got back your homework 1. The grades are turned on online along with the solution, and to be clear with that, I posted the original solution and the corrected solution so you could see what was up. But the corrected solution is obviously the one that we're going to use. Now, you all just turned in homework 2 on Wednesday, so I obviously hadn't gotten that graded yet. Your next homework is due on February 12th. It's a rather short one, but I've covered everything, so you can start it, immediately. There's no reason to hold off on that. Monday, I will open it up for questions on that, and then we will you all turn it in on Wednesday. Next Wednesday, I'm going to give you your last homework before the first exam. So your first exam is going to cover 4 homework assignments. That homework will be on beam design and on slab design, because that's something we haven't talked about yet. But we've got to walk before we can crawl. And so what I want to do today, and I'll go ahead and tell you, today's going to be a little bit like movie time because I'm going to be talking a lot about design. But that's what I want to talk about is design. Remember, so for the past few days we've been talking about just beam behavior, and we talked about the 3 stages of beam behavior. We have beams in their uncracked state, beams in their cracked state, and then beams at their ultimate capacity. And we've actually spent a little bit more time here recently on their ultimate capacity because we've been looking at 2 things. Not only just the MN calc, what is a beam's ultimate flexural capacity, but then we started getting into some more code-specific stuff, like what's beta 1, what are the strain limits in a beam, how does that determine its resistance factor, what's the minimum reinforcement limits. And so I wanted to spend some time talking about that, because once we understand a beam's ultimate capacity and we understand the requirements it's supposed to meet, then we can start talking about design, okay? Now, I'm going to throw a new term at you today, and this term is really, really important for the purposes of design, okay? And it's this term rho, okay? This Greek letter rho, I sort of write it like that. You might sometimes see, it written like that. That's about the best I can do. But rho is what's called a reinforcement ratio, okay? Now, the way that you compute it is you take the area of steel and you divide it by B times D, okay? But what it really is sort of a percentage of reinforcement. In other words, you take the area of steel divided by what I guess you would call the effective area of the concrete. Because we're getting to a point where really what we care about when we're talking about design is the width of the beam, and not the height, but that effective depth, the distance from the top of the beam to where the steel lies. So AS over BD is sort of a percentage of how much steel. So if you have a rho value of, let's say, of 0.02, you can sort of think that 2% of that section is reinforced. That's sort of a way of thinking about it. I will go ahead and tell you that rho values are small, okay? So when we compute rho values in reinforced concrete design, you don't get rho values of like 6. They come out as like 0.0016 or 0.0027. They're small numbers, so be aware of that. But the reason why I'm bringing up rho is because rho is going to become a fundamental parameter that we use in design. The idea is, okay, if I know about how big it needs, how big the beam needs to be, if I know that and I know the reinforcement ratio, that can help guide me towards designing and proportioning the cross section. Okay. Now, what I'm going to do for this design discussion is I'm going to use some of the parameters that we previously defined, but this rho value is going to become pretty important. So another way of expressing rho is to say that the area of steel is rho times BD. That's just me rearranging the fraction. Now I'll go ahead and tell you that these slides are on Blackboard. I actually recently updated them. I tweaked some of the images a bit. So if you downloaded them a while back, I would replace them with what's currently on Blackboard, because what's currently on Blackboard is slightly different. Not a lot, but a little bit. And I also uploaded the next set of slides as well. Okay. Now, I'm going to do a little bit of math with you, a little bit of formulas and substitutions and things like that. So just bear with me, and you'll see what I'm doing here in a second. But give me a little bit of rope because I'm going to throw some algebra at you. Okay, let's go back to some basics with a concrete beam. Okay, when we perform an analysis to determine the ultimate capacity, what was the first thing we did? Well, the first thing we did was we looked at equilibrium. We recognized that the sum of the forces in compression in the beam must equal the sum of forces in tension, right? So the forces in tension were the area of steel times Fy, and then the forces in compression was 0.85 Fc prime times the area of that stress block, which for a rectangular beam was AB. Sound good? And so we use that to solve for A. That was the term we don't know at the beginning of the analysis. We know the dimensions of the beam, we know the concrete's whatever, KSI, 4 KSI, 5 KSI, whatever. We know the steel grade, we know the area of the steel, but we don't know A. So we solved for A. So that was fine for analysis. When I'm talking about design, I want to look at this. Okay, so all I'm doing here is I'm saying, okay, rho is AS over BD, or AS is rho BD. So instead of here where it says AS, I'm just going to replace it with rho BD. Okay? And again, just bear with me, you'll see what I'm doing. So AS is rho BD, so I can develop a new term for A. Notice that the B, there's no B on the denominator because the B is canceled. So I have A is now rho d Fy divided by 0.85 Fc prime. Now what I'm going to do is I'm going to say, all right, let's go back to the moment capacity. What is the moment capacity? AS Fy d minus A over 2. Okay? So I'm going to do some more substitutions. All right? AS is rho BD, so where I have an AS in the expression, I'm going to replace it with rho BD. And the A quantity that I just derived, I'm going to replace that. Okay, so I massage that a bit, do a little bit of algebra, rearrange that, and I come up with this expression right here. Okay, this BD squared Fy times this junk that you see right here. Okay, now here's the point that I'm getting at. Okay, I'm going to rearrange this a bit. I'm going to show you this curve that I see here. So I'm taking Mn over BD squared equals that pile of junk over there. Okay. So on the left, what do I have? I have Mn over BD squared. So Mn is how strong the beam is, and BD squared, if you could think of BD squared as sort of a measure of about how big the beam is, because B is how wide it is, and D is how tall it is. BD squared sort of gives you an idea of how big it is. So basically what I'm able to plot is everything over here on the right, I can plot what happens to the strength of a generic beam as I put more steel into it, right? So think about that. That curve is plotting how strong that is as I put more steel into it. Now, look what's happening. The curve's going up, and it's like, well, duh, you know, you put more steel into the beam, it's going to get stronger, right? I don't think that there's anything that's very mysterious about that. You put more steel reinforcement into a concrete beam, it can hold up more load. But it's not as simple as that, okay? Remember, I don't care about Mn, I care about phi Mn, okay? So Mn is the nominal moment capacity, but phi Mn is what happens when our capacity is adjusted by that safety factor, okay? Well, remember, phi is not always 0.9. Phi changes. There's a transition region, okay? And so what happens is, remember, our phi value has 3 regions. We have a tension control, then we get into this transition region, and then we get into compression control. So this right here, this is our tension region. This is our transition region, and this is compression control. Look what's happening here. You're dumping all this steel, so we have a reinforcement ratio of about 2% to about, you know, I don't know, this is probably about 1.6% to maybe like 2.8%. So as you keep dumping more and more steel into the cross-section, you actually don't really get any benefit out of it. You keep dumping all this steel into the shape thinking you're going to make it stronger. Yeah, you're making its nominal capacity stronger, but you're not making its usable capacity any larger. So what that means is there's really no point in dumping all that extra steel. So in reinforcement land, like there's sort of, I'm sort of trying to teach you a lesson off to the side. You're going to be in design land, and you're going to be an engineer and you're going to be designing a building, a bridge, or something like that, and you do the math and you say, here's your design. And there's going to be some contractor, some boss of yours that says, yeah, why don't we throw a couple more rebar in there just to be on the safe side? That doesn't necessarily mean that it's actually performing any better. You could be at a point where you're dumping all this steel into the section, you're literally not getting any bang for your buck. So don't do that, okay? Trust the math. Just do the math correctly. So does that make sense? Okay, all right. Now, that aside, I'm going to take this expression here, and I'm going to solve, I'm rearranging that expression a bit, and so I'm rearranging it, and I'm solving for BD squared. So going from the top to the bottom, all I'm doing is I'm saying, all right, let's rearrange that, solve for BD squared, and massage it algebraically to make the equation a little more palatable. And so what you see there in that box is just BD squared expressed a little more simply. Now, that equation looks complicated, but it's actually a remarkably, beautifully simple expression for design. Because what's going on in that expression? Well, I've got BD squared equals a pile of junk, okay? So as a designer, what I'm saying is, if I'm a designer, I want to know how big the beam needs to be. And what this equation is saying is, here's how big the beam needs to be, and it needs to equal all this crap. Okay? So what's going on the right side of the equation? What's on that side that I need to know? Well, I see a bunch of FC primes and FYs, right? But I can assume that at the beginning. I can say, okay, I need to design this beam. I'm going to use grade 60 steel and 4 KSI concrete. Boom. Those values are constants. Okay? MN. Now, I don't know MN because I haven't designed the beam. But go back to homework 1. What did we do on homework 1? We were given a floor system, and we took that floor system and we determined how much moment was on a given beam, right? So wouldn't that tell us how much moment that beam needs to be able to withstand? So we can sort of determine how much of this we need based on our structure, right? It's a beam that's 22 foot long. It's got 1 kip per foot in dead load and 3 kips per foot in live load. So I can do the analysis and get a factored moment, and that can help me determine how much required MN I need. So that's actually pretty doable as well. The one thing that's a little iffy is rho. So how do you pick a rho value? Well, again, what is rho? Just to make sure we're all clear, is AS over BD. They are very simple terms that serve a really, really useful purpose for design. Now what we can do is a couple things. We can choose a rho so that we hit a target strain value, which is a little more complicated, or we can use a rho value for design purposes. And when you're just starting out with design, I sort of recommend that. In fact, if you go back in the spec, like, to be clear, structural design specifications, they change. They're evolving documents. It's not like the document that you use today is the one that's always going to be the case forever. You're always going to have different factors, different equations, different expressions. That's just the nature of our field. Engineering is an evolving community, so it always changes. There are some behavioral patterns that pretty much I could tell you aren't going to change. I would be highly shocked if during my career as an engineer, if we stopped using 0.85 FC prime. I don't think that's changing anytime soon. But there are some nuances with strain limits and things like that. A while back, in a few previous editions of the spec, there was a limit of this. In other words, you had to design your beam such that your reinforcement ratio was met by this limit. We have since removed that from the spec. It's no longer a limit that we have to meet. However, it is a very, very useful value for design. In other words, if I'm in design mode and I don't have a clue what this beam needs to look like, I could use that to start out. I'm going to have to go back and check all of my current ACI limits and things like that, but it's a really good place to begin your design computations. And so, unless otherwise stated, I would use this for design purposes. That is one row value that you could use for design. Another row value that you could use would be, okay, give me a reinforcement pattern that'll generate a target strain value. So I can say, okay, I want the strain in the steel to be 0.01. So I plug that in here. If I know what I want my strain value to be, maybe I'm doing that so I can ensure I'm not going to have to go back and iterate my phi value, or I really don't want to have to do that. I could say, okay, plug in a strain value of 0.001. That gives me a C over D ratio. I can take that C over D ratio, compare it to this, because remember, A equals beta 1 times C, and I can take this and I can say, okay, if I know my target strain value will give me this. This can tell me what my reinforcement ratio needs to be. So that's one way of designing. I don't want to say it's the more complicated. It's a little bit more of a refined approach where you're being maybe a tad more scientific. And I'm okay with that, but I do recognize, hey, we're engineers. We just want a beam design that makes sense. So that's another option as well. So like I said, you can do a little bit of algebra and massage that expression a bit and come up with a reinforcement ratio to achieve a target strain value. And I will say it is a pretty simple expression, because all you need is you need a desired strain value and you need an FC prime and an FY. And if you have FC prime, you can determine that. So you can just plug and chug that one as well. So pretty straightforward stuff. Now, sound good? All right. What I'm going to do is we're going to outline a checklist. Okay. Now, before I do you all have the beam design rebar charts that I gave you? Y'all have those? I'm going to borrow Miss Roberts. Y'all have this with you? Okay. Get that out, because we're going to use that today. Yeah, that. Okay. All right. So what we're going to do is we're going to outline the procedures for design. Now, this slide has two types of designs. We have unknown cross-sections and we have known cross-sections. What is the difference? Okay. Well, an unknown cross-section is when you are starting from absolute scratch. You have no idea what the beam looks like, and so you need to determine the width of the beam, you need to determine the depth of the beam, you need to determine the area, you got to determine everything. Okay, so it's the total start from scratch mode. Okay, that's the design of an unknown cross-section. What about the design of a known cross-section? Well, the design of a known cross-section is when you do know what the beam looks like. You know how wide the beam needs to be. You know how deep it needs to be. And in a known cross-section problem, the only thing that you need to determine is how much steel you're putting in. Okay? Now, I'm sure some of you are like, now hold on, Dr. Mike. When are you ever going to know what the beam looks like? If you're in design mode, aren't you clueless? Well, it depends on the design. Okay? There are two real common instances where you would know what the beam looks like. The first is if you're dealing with a precast element. You go to a precaster and they have ready-made forms, and you know the form sizes that you're going to use, and you know the increments that they're going to select, and so all you need to do is pick the reinforcement pattern. Very real option. Another known cross-section problem is the design of a slab, a one-way slab. That probably doesn't make a whole lot of sense right now. It will later, but suffice it to say that we choose our depth of our slab based off of minimum ACI requirements, and the width of our slab comes from our design assumptions, so we really don't need to worry about that either. So when we design a slab, we design assuming a known cross-section. What I'm going to do is go through the procedure for an unknown cross-section, okay? So there's a lot of steps here, so I'm going to take it one step at a time to make sure everybody's clear on this. So if you notice, like, I've got here, this is a cross-section and the steel unknowns, like step 1, step 2, step 3, step 4. And then we're going to do an example, and we'll go through it start to finish, okay? And so I want you to know that these steps are really, it's not like this is magic, or it's like, you know, this is the procedure outlined in the spec. All these are just taking the the design expressions that we've come up with and the limits, and putting them in an order that makes sense for design. That's all this is. Okay, so what is step one? Step one is to compute the factored moments on the beam. In other words, do your structural analysis, right? I need to know what I'm designing the beam for. I need to know its factored moment. It's WL squared over 8 if it's a simply supported beam, uniformly distributed load. Now, problem with this is that if I'm in design mode, look right here. So I've got a floor system, and I've got a beam, let's say, running from this column to a column over here, and I need to determine the load on this beam. Well, I don't know what the beam self-weight is because I don't know what it looks like, right? I don't have a clue what it looks like. I haven't designed it yet. So I have to assume a beam's self-weight. Now, there are two ways to assume a beam's self-weight. The first is to literally just guess a value, okay? And at your stage as students, probably wouldn't work very well because that's just something that you get with experience. You design 100, 200, 300 beams, you'll start to get good at this. You'll look at a given problem and say, that beam probably going to weigh about 200 pounds per foot, so I'm going to guess that value. Honestly, it really doesn't matter what value you guess because in the end you have to take your assumptions and verify them, but the better your assumption, the less chance that you're going to have to iterate your design. In other words, you guess some values, you come up with a design, you check it, you go, oh man, that beam's not good enough. Now I got to tweak that size of it and check it again. Then I got to tweak it and check it again. That's iteration. So the better you get at these assumptions, the less chance that there is you have to do that. Okay? So instead of just guessing, picking a value out of the sky, you can use ACI requirements that'll help you guide this out. So for example, if you're using regular old normal weight concrete, what this right here will tell you is what is the minimum height required for the beam, and this is really for deflection considerations, but ACI specifies that your beams must be at least this tall under various instances. So for instance, let's say you have a cantilever beam, okay? So the beam is 20 foot long, okay? If you have a 20 foot long cantilever beam, take that length, divide it by 8, that tells you how tall the beam needs to be. That's your height, okay? Now, if you then say, okay, the beam's this tall, maybe it's half as wide, boom, there's the size of your beam. So you can come up with a reasonable guess for how heavy the beam is. It's probably not going to be the final answer, but it's close enough to at least get you an MU value to get started. Okay, so, and again, if you have a continuous beam or one end continuous or simply supported, you can use a similar assumption. And I have some adjustments to what's going on in this table if you have other conditions. So for instance, if your Fy is not 60,000 psi, take whatever you have here and multiply it by that. If you have a lightweight concrete, so it's anywhere from 90 to 115 pounds per cubic foot, remember what are we assuming for normal weight reinforced concrete? Usually like 150. So if you have a really, really lightweight concrete, you need to multiply what you get here by that. And if you have something that's like a combination, just go with what's most conservative, which is going to be that one right here. Sound good? Now, where does that give you? That will tell you what MU is, right? Well, what do we know about MU? Well, phi has to be greater than or equal to MU. So if I know what MU is, I can say, well, MN, or in other words, my required MN has to be MU over phi. So what I've got to do here is I've got to compute my required MN, and I have to assume that phi is 0.9. Now remember, phi changes depending upon the strain in your steel, so this is something I'm going to have to go back and verify. My beam has to meet this limit anyways, but keep in mind, we're in design mode. We have no idea what the beam looks like, so we have to verify that. Now, next thing that we got to do is we got to compute a reinforcement ratio. So one reinforcement ratio you could use is this, is 0.18 FC prime over Fy. You could also use that. Just choose a target strain value in your steel and use that. And that could be your reinforcement ratio, whichever one you want. For simple, straightforward stuff, I usually use that. Once you've got your reinforcement ratio, You know your material properties. You got MN. You can calculate your BD squared. That'll tell you about how big the beam needs to be. Based on that, you can say, all right, I can determine with BD squared what the required size of the beam needs to be. And so I'll choose B and D values for a trial section. I'll set the, one of the things about concrete beam design, I am not going to design a beam that is 14.38639 inches wide, okay? Somebody is going to go to Home Depot or the lumber, 84 lumber and buy some lumber to create formwork for these beams, okay? So I am not going to go tell a contractor that beam needs to be 14.386 inches wide. I'm going to keep it simple, say it's 14 inches, 16 inches, 15 inches. I usually set my beam dimensions to 1 inch increments just to keep it simple, okay? Now, I'm choosing B and D. The total height of the beam is usually going to be the depth plus about 3 inches, okay? And the reason why is this. Let me erase this. I'm going to pull this up here in a second, but here's the concrete beam. Okay, this is the bottom of the beam, so let's say I've got my steel here, okay? Well, that steel doesn't just magically float in space in there. First off, there's going to be some chairs that hold this, this rebar in place as you place the concrete, but we're also going to have some bars that wrap around the steel like this. For now, just know that they are there. Later on, we will design those bars. The short answer is these bars here, these ones, are helping to resist moment. But these, which we call stirrups, are put there to resist shear. Okay? So you have a beam that has a shear diagram and a moment diagram. These things are improving the concrete beam's shear capacity. So if you look at the rebar cage inside of a concrete beam, I'm going to skip ahead a few slides, just to show you kind of what it looks like. Ooh, I got to skip way ahead. I think this is kind of important. This is sort of like what the rebar cage inside of a typical beam would look like. And so right now we've been focused on these bars down below. Those are the beams, or the bars resisting the moment. But these sort of ties going along like that resist the shear. Okay. One of the things you can kind of notice on this image, I've got a simply supported beam. Notice how there's more of these near the support and less of them in the middle. Why is that the case? Well, the reason is because of that. There's your shear diagram. There's less shear in the middle, so you need less of them in the middle than you do on the outside. So we'll detail those later on. All right. I have a lot of slides, and I'm sure some of you are seeing this like, oh God, this is horrible. It is. No, I'm just kidding. I'm kidding. All right. So, okay, here's where I was at. So, we can choose the B and D values for the section. Remember, the top of the beam down here, that's D, and then the top of the beam here, that's H. Typically, we say that for most beams, that dimension right there is about 3 inches. That can change if you've got like really, really large rebar, or you've got concrete elements in other applications. So, for instance, that dimension might change if you've got a concrete structure that's outside, or maybe if you're designing a concrete beam over like a pier in Seattle where there's a lot of brackish water, and so as a function of corrosion, we require more surrounding concrete. We call that cover, and I'm going to talk about cover here in a second, but that's sort of where that comes from. But a basic assumption for most interior beams in commercial building structures is a D plus 3 inches. Once you know how big the beam's going to be, you can say, okay, row BD will tell me the area of steel that I need. I pick a reinforcement pattern, and boom, I have a beam. Am I done with the problem? No, I'm not done with the problem. I made a lot of guesses and a lot of assumptions to get to that point where I knew about how big the beam needs to be and about how much reinforcement's in there. So I need to go back and analyze that section and verify my assumptions, verify that I'm meeting ACI requirements, and verify that VMN is greater than or equal to MU. Sound good? Okay, let's talk about cover. So one of the things that I want to make sure that you get out of this class is a little bit of a dose of reality. In other words, I can show you math and equations all day long, but I want to make sure that you understand the real-life ramifications of what you're talking about. Now, in short, what cover is the clear distance between a piece of reinforcement and the external layer of concrete. So for instance, if I'm talking about some mass of concrete and here's a piece of rebar in it, cover is that dimension right there, or that dimension right there. In other words, how far must I embed that piece of rebar into the concrete? Now, first off, we have limits for really two reasons. We want to make sure that the rebar is far enough in the concrete so that we get the strength out of the rebar that we would like. That's obviously an important reason. But I'd say that what's a more important reason for most cover requirements is the idea of corrosion. I don't know if you know this or not, but metal rusts, okay? And when metal rusts, what does metal do when it rusts? Anybody know? When steel rusts, I mean, obviously it gets brown, it gets gritty, but what else does it do?
It breaks apart.
It breaks apart.
Corrodes.
It corrodes, but when metal rusts, it expands. It actually increases, the volume increases. Now, think about it like this. I have a beam, I have rebar embedded in the beam, the rebar is corroding. Rebar expands. What happens then? We start cracking the beam, and we can start having some very serious problems, okay? When you start looking at, if any of you have ever been on any DOH jobs and you see a concrete beam and it has some significant cracking, there's a good bet that maybe that reinforcement's starting to corrode. That once there's some water or some chloride penetration on that rebar and it starts to corrode, the concrete cracks as a result, and then that cracking leads to a larger void, which leads to more water and chloride penetration, which leads to more corrosion, which leads to more cracking, and so it just sort of builds on itself, and it gets out of control. So it's a bit nuts. DOH is one big thing in our world in structural engineering. A big area of research is to try and develop means and methods to reduce corrosion. There's a process that gets used every now and then called electrochloride chemical extraction, where basically what they do is they attach jumper cables to either end of the a piece of reinforcement sticks out, stick a cathode on it, and use, it's almost like reverse electroplating, and they pull the corrosion out of the steel. Like if you ever are on YouTube and you're bored, you'll see these videos where folks find this like antique wrench and it's all corroded and they restore it. And one of the ways that they get the rust off is they stick it in, a bath full of water and salt, and they put an old rusty piece of metal on it and attach a car battery to it, and all the corrosion gets sucked to the to your scrap piece of metal, and the wrench that you wanted to restore, all the rust is off of it. And so that's one way that a lot of these DOHs do that. Of course, in order to do that, you have to have something to stick the rebar onto. Okay. Now, dependent upon, so I guess the overall point I'm making is that dependent upon your application, your cover can change. For example, in West Virginia, for bridge decks, the cover on the bottom of the deck is 1 inch, but on the top of the deck is 2.5 inches. In other words, here's the driving surface, here's the tires, the rebar has to be 2.5 inches below the surface. Now why would we care about the rebar being 2.5 inches below the top, but only 1 inch from the bottom? What do we put on the top of bridge decks on days like today? Salt. We put de-icing salts, chloride penetration into the concrete increases chances of corrosion. So that's why cover for the top of decks is usually more. So if we have something, exposed to the weather or contact with the ground, the cover requirements are going to be a bit more stringent. For internal beams in buildings and things like that, your primary reinforcement cover, your stirrups ties, usually the cover is about 1.5 inches. All right. Why is that important? Well, here's the thing. I think that this table makes a lot of sense, but I haven't really explained that table. Okay? So let me explain that table. So here's like a typical reinforced concrete beam. Okay? Let me ask you a question. Let's say I had a beam that was 6 inches wide, and I said I was going to put 12 number 14 bars in one layer in that beam. What would you say? If it's 6 inches wide, and I'm going to put 12 pieces of rebar that are number 14s. You're shaking your head. Why? Why?
It's too much area.
It's too much. It's not going to fit, right? So that's exactly right. So let's say here, okay, let's say I was looking at this beam, and I've got 3 bars, okay? Well, in order for this option to work, this width has to be a certain value, okay? Well, how do I determine that? Well, I've got the cover on each side, which we'll say is 1.5 inches for interior beams. I've got the stirrup, and typical stirrups are either going to be number 3 stirrups or number 4 stirrups. That's pretty common with structural design, unless you got some really hefty shear load, which usually isn't the case for most interior beams. So I got 1.5, 1.5. I got a number 3. What's the diameter of a number 3? 3/8. So I got 2 3/8 inches on each side. I've got 3 of these, so whatever the diameter of that is. And then I've got these dimensions here, these spacings. What are these spacings? Well, those spacings are the maximum of these 3 quantities, either the bar diameter that I'm looking at, 1 inch, or 4/3 times the maximum aggregate size. So in other words, if you have concrete, let's say it's your maximum aggregate, you're using like a number 57 stone, you got to have enough space between the bars so that the concrete can actually get in between them, right? So what'll happen is, based on your reinforcement pattern, what you can do is, okay, if I'm going to use 5 number 7s, I can determine how wide that beam needs to be so that I can actually fit 5 number 7s in there. Make sense? So that's what I've got here in this design aid. We're going to call it after this, but let me pull this up. Oh, up one there. So here's my design aid. So here's my bar area. So the way that this will work, we're going to pick a series of reinforcement patterns, and then we're going to check that against this. So if I have a beam and I'm going to use 5 number 7, let's say number 7 rebar, that beam has to be at least 12.75 inches wide, and that's the 1.5 inches of cover. That's your stirrups on each side, and then think. 5 bars, so I got 5 bar diameters, I got 5 bars, I got to have 4 spacings. So take all that and add it up, it comes out to 12.75 inches wide. So what we'll do is we'll pick a family of reinforcement patterns up top, and then we'll check it to see, okay, for our problem, are these patterns even going to work? Are they going to fit inside the beam that we design? And if not, we'll move on to the next one. And so what will happen is we'll have a beam design problem, we'll probably pick like 4 or 5 different reinforcement patterns. 2 of them might not work because they're not going to fit, and of all of the 3 reinforcement patterns, what do? We pick the one that has the least amount of steel. And that is how we go about design. What we are going to do on Monday is we're going to do a full-blown reinforced concrete design problem. We're going to design a 22-foot long beam that has a dead load of about 1 kip per foot. That is on top of the beam self-weight. So if the beam weighed like 300 pounds per foot, the total dead load would be like 1.3 kips per foot. So there's the dead load, and then there's the live load, what the beam's being used for. So let's say it's a beam in an office building or something like that. So it's got 2,000 pounds per foot of live load. That live load is already reduced, so we don't have to worry about the live load reduction. We're going to use 4 KSI concrete, we're going to use 60 KSI steel, we're going to use regular old concrete with a normal weight of 150 pounds per cubic foot, and we're going to use an approximate D/B ratio of 1.5. So, this dimension to that dimension is about 1.5. There's nothing that tells you in design land that you have to use that. You could tweak that if you want as the designer. Really, the only limit that you have as a structural engineer when it comes to beam depth, quite frankly, is your contractor and your architect. In other words, if you only have, I don't know, 18 inches between that drop ceiling and the next floor, well, you only got 18 inches to put a beam there, you know, so you got to fit your beam there. But other than that, as long as you're safely resisting the load, that's what matters. We're going to do a full-blown example start to finish. Then we're going to look at designing for a known cross-section. This example will take us every bit of Monday, maybe even a little bit of Wednesday. So this is going to be a big one. Be safe getting home if you're headed home, although the roads look pretty clear. So I guess stay warm. I will see you all if you're leaving on Monday. If you're leaving, have a great week.